Every GPS satellite orbiting Earth, there are dozens of them, circling 20,000 kilometers above your head at 14,000 kilometers per hour, has a clock built into it. Before engineers launch these satellites, they program the clocks to tick slower than identical clocks on the ground. Not by much, just 38 microseconds per day. But they must do this, or the system fails. Why? Because clocks in orbit run faster than clocks on Earth. Not because they're broken. Not because of some engineering quirk. Every clock, atomic clocks, mechanical clocks, your heartbeat, radioactive decay, runs faster up there. Why does a clock 20,000 kilometers up tick faster than one on the ground? What does gravity have to do with how fast time passes? Is time even the same thing everywhere? You've probably heard the answer. Gravity slows time, or gravity warps spacetime. But that's just vocabulary. That's renaming the mystery, not explaining it. The reason has nothing to do with time being affected by gravity. It's about what time is. The GPS problem is real and immediate. If you don't correct for this time difference, if you just let the satellite clocks run at their natural rate, your GPS position drifts by about 10 kilometers per day. This isn't measurement error. This isn't clocks malfunctioning. It's a physical effect that every engineer working with satellites must account for, or the technology simply doesn't work. There are actually two competing effects. The satellites are moving fast. Special relativity says moving clocks tick slower. That would make the satellite clocks run slow. But the satellites are also farther from Earth's gravity. General relativity says clocks in weaker gravity tick faster. That would make them run fast. The gravity effect wins. Net result: satellite clocks gain 45 microseconds per day compared to clocks on the ground. Engineers compensate by programming them to tick slower before launch. But how does gravity reach up there and speed up a clock? The usual answer goes like this. Gravity warps spacetime. Time flows slower in stronger gravitational fields. The satellite is in a weaker field, so time flows faster there. But what does that mean? Warp spacetime is just another way of saying affects time. It's circular, like saying fire burns because of combustion. You're using one mysterious phrase to explain another. Here's a sharper question. What is spacetime such that mass can warp it? And why does warping mean clocks tick differently? It's not that gravity is pulling on the clock mechanisms. It can't be, because every type of clock slows down identically. Mechanical pendulum clocks, atomic clocks based on electron transitions, light clocks, even radioactive decay. Completely different physical processes. Gravity affects them all the same way. What do all these processes have in common? They all unfold through time. But what is time? Einstein figured this out in 1907, sitting at his desk in the patent office in Bern. He called it the happiest thought of his life. Imagine you're falling off a roof. While you're falling, you feel weightless. You drop a coin from your pocket. It floats beside you, not moving relative to you at all. Not because there's no gravity. The Earth is still pulling on both you and the coin. But you're both falling together, accelerating together, so relative to you, the coin floats. Here's the crucial insight. You cannot tell the difference between free fall and floating in empty space, far from any gravity. Cannot. No experiment you could do would distinguish them. This is the equivalence principle. What you feel as gravity when standing on Earth, your weight pressing into the ground, is indistinguishable from the feeling of being accelerated. like being pushed by a rocket. If gravity and acceleration are equivalent, and we know from special relativity that time behaves strangely during acceleration, then time must behave strangely in gravity too. But that's still just saying that it happens, not why. Stop thinking of time as an invisible river flowing forward. Time is what clocks measure. But what are clocks measuring? Intervals between events. Light bouncing between two mirrors. That's an interval. An electron jumping from one energy level to another. Interval. A pendulum swinging from here to there. Interval. All these processes are comparisons. One event happens, then another event happens, and you count how many times that repeated. Here's the thing. Those intervals depend on the path you take through space-time. Not through space. Through space-time. Imagine two people walking from your house to a store. One takes the straight route, 1 kilometer. The other takes a winding path through the park, 3 kilometers. They both end up at the store, same location, but they traveled different distances, different path lengths through space. Same thing happens with time. Except, and this is crucial, in space-time, the straight path means more time elapsed, not less. It's reversed from space. A clock in free fall, like a satellite, takes a straighter path through space-time. More time elapses on that clock. A clock on the ground, held still by the Earth pushing up on it, takes a more curved path through space-time. Less time elapses. Time isn't something that flows and gets slowed down by gravity. Time is the length of your journey through space-time. Different paths, different lengths. Let me make this geometric picture more precise. Space-time is a 4-dimensional fabric. 3 dimensions of space, 1 of time. When mass exists, it creates curves in this fabric, not a metaphor. Literal geometric curvature, like hills and valleys on a landscape, except in 4 dimensions. In curved space-time, a straight line isn't what we normally call straight. The technical term is geodesic, the path that maximizes the elapsed proper time. Objects in free fall follow geodesics. They're taking the straightest possible route through curved space-time. Now here's the part that flips everything around. When you sit in a chair on Earth, you are not following a geodesic. The chair is pushing up on you constantly. You are being accelerated upward, away from the geodesic you would naturally follow if you were falling. You're being forced off the natural path. The satellite in orbit. It is following a geodesic. It's in free fall around Earth. That's what an orbit is. Continuous free fall. The satellite is in its natural state. This is completely backwards from intuition. We think we're at rest, sitting here, and the satellite is moving. Actually, the satellite is in the natural state of motion through space-time. We are the ones being constantly accelerated off that natural path by the ground beneath us. Because we're being pushed off the geodesic, our clocks tick slower. The satellite, following the geodesic, has clocks that tick faster. As Einstein put it, matter tells space-time how to curve, and curved space-time tells matter how to move. Imagine a simple clock. 2 mirrors facing each other vertically, with a pulse of light bouncing between them. Each round trip is 1 tick. On Earth's surface, space-time is curved by Earth's mass. The light pulse travels through this curved geometry. From the light's perspective, the path is longer because it's moving through curves. It takes more coordinate time for each round trip. The clock ticks slower. Up in orbit, where gravity is weaker, space-time is less curved. The light's path is closer to straight. The round trip takes less coordinate time. The clock ticks faster. This is the critical point. This effect applies to all clocks the same way. Not just light clocks. Atomic clocks depend on electron transitions. Mechanical clocks depend on pendulum swings or spring oscillations. Radioactive decay depends on quantum tunneling, completely different physics. But they all happen in the same curved spacetime, so they all slow down by exactly the same factor. We measure this. GPS satellites are 38 microseconds per day faster than ground clocks after you account for the slowing from their speed. The prediction from general relativity matches the measurement. Exactly. This is tested technology, working in your phone right now. So mass curves spacetime. But how? What's the mechanism? Einstein's field equations, published in 1915, are the answer, or at least the mathematical answer. On the left side of the equation is the curvature of spacetime, described geometrically. On the right side is the mass and energy content. The equal sign means mass determines the geometry. Not that mass sits inside some pre-existing geometry. The mass literally creates the geometry around it. Think of it this way. Empty spacetime with no mass or energy in it is flat. This is called Minkowski space, the spacetime of special relativity. Now add mass. The spacetime curves around it. People say it's like putting a bowling ball on a trampoline, creating a dip. Except spacetime isn't sitting on anything. It's not embedded in some higher dimensional space. It curves intrinsically. The angles inside triangles don't add up to 180 degrees. Parallel lines converge or diverge. The geometry itself changes. Near Earth, space-time curves significantly. As you go farther from Earth, the curvature decreases. At satellite altitude, 20,000 kilometers up, there's less curvature. At infinity, the curvature approaches zero. You get back to flat Minkowski space. The difference in curvature creates the difference in time flow. Stronger gravity, more curvature, slower clocks. Weaker gravity, less curvature, faster clocks. The time dilation factor is given by the square root of 1 minus 2 gm over rc squared, where g is the gravitational constant, m is Earth's mass, r is your distance from Earth's center, and c is the speed of light. The larger r is, the farther you are from Earth, the closer this factor gets to 1, meaning time passes at the normal rate of flat spacetime. The measured value matches this prediction exactly. Consider the twin paradox, but with gravity instead of speed. Twin A stays on Earth. Twin B moves to the top of a mountain. They both live there for 80 years. When they meet again, Twin B has aged more. Not by much. We're talking about 90 microseconds over 80 years. But it's measurable with atomic clocks. This has been tested. In 1971, Hoffel and Keating flew atomic clocks around the world on commercial jets and compared them to clocks left on the ground. The results matched relativity's predictions. In 2010, researchers at NIST measured time dilation with clocks at different heights separated by just 33 centimeters, about 1 foot. They detected the difference. Think about the implications. Your head ages faster than your feet, only by nanoseconds over your lifetime, but it's real. Every atom in your head experiences slightly less gravity than every atom in your feet. Slightly less spacetime curvature, slightly more elapsed time. This seems absurd. How can the same person age at different rates in different body parts? The answer is, they do. It's just imperceptible at human scales because Earth's gravity is weak and the distances are tiny. But near a black hole, the effect becomes enormous. Imagine someone falling toward a black hole's event horizon. To an outside observer, watching from far away, they appear to slow down. Their clock appears to tick slower and slower as they approach the horizon. It would take infinite coordinate time, as measured by the distant observer, for them to actually cross the horizon. From the falling person's perspective, though, they cross the horizon in finite time. Their own clock ticks normally from their point of view. They just reach the horizon and fall through. Different paths through space-time. Different elapsed times. Same geometry. Different viewpoints. Let's circle back. We started with GPS, satellites ticking faster, 38 microseconds per day, faster than clocks on the ground. Now you understand what that means. Time is geometric. It's not a flowing substance. It's not a universal metronome in the background. Time is the length of your path through space-time. Different paths have different lengths, different elapsed times. Space and time aren't separate things. They're unified into space-time, woven together. Just as the distinction between east-west and north-south depends on how you orient yourself, they mix together under rotations. The distinction between space and time depends on your motion. They mix together under what we call Lorentz transformations. Time is the fourth dimension. Gravity curves all four dimensions together. You cannot curve space without curving time. They're locked together. Newton thought there was absolute space, absolute time, and gravity was a force transmitted instantly across space. He was wrong on all three counts. Space is relative. Time is relative. They depend on your motion and on the gravitational field you're in. And gravity isn't a force. It's geometry. This changes the entire framework. Clocks don't tick at different rates because gravity somehow slows them down, like friction slowing a machine. Clocks tick at different rates because they're traveling different distances through curved space-time. It's pure geometry. We know how mass curves space-time. Einstein's equations tell us the relationship. We know that mass does curve space-time. Every measurement we've made confirms it. GPS wouldn't work if we didn't account for it. But why does mass curve space-time? There's no answer yet. It's a relationship we've discovered, not something we've explained at a deeper level. Newton discovered that masses attract, the law of gravitation, but he couldn't say why. He just said, that's how they behave. Einstein discovered that mass curves space-time, but he couldn't say why. He gave us the equations that describe the relationship, but not the underlying reason for it. This is the quantum gravity problem. General relativity, the theory of curved space-time, works beautifully at large scales. Planets, stars, galaxies, the expansion of the universe. Quantum mechanics works beautifully at small scales. Atoms, particles, fields, but they're incompatible at the extremes. At black hole singularities, where curvature becomes infinite. At the Big Bang, where the entire universe was compressed to quantum scales. At the Planck scale, where quantum fluctuations should make space-time itself uncertain. We don't have a unified theory yet. Our understanding is incomplete. Time dilation is real. It's measured. It's used in technology every day. But the deepest question, why mass and space-time are related this way, remains open. Maybe space-time emerges from something more fundamental. Maybe we need entirely new concepts to understand it. GPS satellites tick faster, 38 microseconds per day. Not a malfunction, not an error. It's a consequence of curved space-time geometry. Engineers program in the correction before launch, or your GPS navigation fails. Time isn't a universal backdrop to the universe. It's a participant in the physical world. It changes with motion. It changes with gravity. It changes with geometry, which raises a question. If time slows down near mass, what happens at the event horizon of a black hole, where gravity becomes so strong that space-time curvature approaches infinity? From outside, it looks like time stops there. Anything falling in appears to freeze. But what happens if you fall in? That requires understanding what happens when curvature becomes extreme. Different story. I've got to stop somewhere.